And now we are in Chapter 2, Radiation Physics. The learning objectives for this chapter will be to define the key terms associated with radiation physics, to identify the structure of the atom, describe the process of ionization, discuss the difference between radiation and radioactivity, list the two types of ionizing radiation and give examples of each, and to list the characteristics of electromagnetic radiation. The purpose of this chapter is going to be to present the fundamental concepts of atomic and molecular structure, to define and characterize X radiation, to introduce the X-ray machine, and we're going to describe in detail how X-rays are produced. This chapter is also going to include a discussion of the interactions between X radiation with matter. A lot of your National Board exam questions will probably be pulled from this chapter. If there were ever a chapter to really hone in on and really understand fully, it's going to be this one. All right, so here we have atomic and molecular structure. We're going to be discussing matter. Matter is anything that occupies space and has mass. Remember from high school, middle school science classes, the three main types of matter are gas, solid, and liquid, right? But we're going to go even smaller, down to atoms and molecules. Um, when matter is altered, when those atoms are altered, energy will result. And an atom is a fundamental unit of matter. All matter is composed of atoms. Okay, so atoms are made up of a nucleus and orbiting electrons. The identity of the atom is determined by the composition of the nucleus and the arrangement of the orbiting electrons. You can see here all of the identities, the number of atomic mass and weight and things like that are found on the periodic table of elements. We don't really have to memorize any of these, but we do need to understand how these numbers relate to how atoms are composed. The nucleus in the atom is composed of protons and neutrons. Protons have positive electrical charges. It's very easy to remember. Protons, positive. Neutrons carry no electrical charge. Neutrons, no electrical charge, or neutrons, neutral. Most of the space around the atom, or most of the atom, is actually empty space. Every atom has a nucleus, and the force holding that nucleus together is called nuclear binding energy. The number of protons and neutrons in the nucleus of an atom determines its mass number or atomic weight. The number of protons inside the nucleus equals the number of electrons outside the nucleus and determines the atomic number. Atoms are arranged in increasing atomic number on the periodic table of elements. We don't need to remember the periodic table of elements. What we mainly need to learn from this is that the number of protons and the number of electrons are equally balanced, and keeping each other in check, they stay neutral. But when we lose electrons from those outer shells, then that means that we have too many protons and not enough electrons, and we end up having a positive charge. It is also important to remember later that the nucleus of an atom, is not going to be affected by X-rays. Only the electrons will be affected by the X-rays. Okay, so here are those electrons. Electrons are tiny, negatively charged particles, and they are zooming around that nucleus. They have very little mass, approximately 1/1800, as much as a proton or a neutron. Electrons travel around that nucleus in well-defined paths, which are known as orbits or shells. If we pretend for a moment that the nucleus is the sun, all of these little electrons are like little planets orbiting around, and they have something called a binding energy, which is what is holding those electrons in their orbits. The shell located closest to the nucleus has that highest energy level. The energy on the outer shells is actually much, much lower. The amount of energy it takes to break off one of those little electrons is equal or greater than the amount of energy that is holding them onto the nucleus. The outer layer of electrons can be disrupted during dental radiography. This is actually how X-rays are made. We shoot this energy at these atoms and we break those electrons off and we use those in order to create photons later. Every type of atom has a different number of electrons, giving each atom a different overall characteristic. All right, so here's that binding energy. Electrons are maintained in their orbits by electrostatic force between the positive nucleus and the negative electrons. This is known as binding energy, holding those electrons onto the nucleus. The binding energy is determined by the distance between the nucleus and the orbiting electron. The strongest binding energy is found closest to the nucleus, and that is in the K shell, and it is measured in electron volts or kilo electron volts, depending on how big it is. So just to reiterate, the electron binding energy is what is holding those electrons in the shell. In case you haven't noticed, I've said it 4 separate times. You'll probably see it on a quiz. You may even see it on your board exams. Okay, so here's where we use those atoms to make up molecular structure. Atoms are capable of combining with one another to form molecules. Molecules are two or more atoms that are joined by chemical bonds or the smallest amount of a substance that possesses its characteristic properties. Here we can see H2O or water. This is a molecule where the two hydrogen atoms are sharing those electrons in their outer shell, which is their only shell, and they are sharing it with oxygen. And we can see that oxygen has 6 electrons on its outer shell and 2 electrons on its inner shell. Actually, every atom only has 2 electrons on its inner shell. That is absolutely a rule of atoms. But here we can see how those 2 hydrogen atoms are staying put with that oxygen because they're sharing those electrons. And here we can see that, again, the molecules can be formed in 2 separate ways. Either they are transferring their electrons back and forth, or they are sharing those electrons between the 2 outermost shells of atoms. Okay, so ionization. This is a very important topic. Ionization. Now, normally, most atoms are neutral, right? We talked about that, where if they have the same number of protons as they have as they have electrons, then they stay neutral. And a neutral atom contains an equal number of protons and electrons. An atom with an incompletely filled outer shell attempts to capture an electron from an adjacent atom. This is important because when enough energy is shot toward an atom and that ejected electron shoots off, as you can see here in this picture, it becomes a negative ion. The remaining atom becomes a positive ion, right? Because now it has 2 positives and 1 negative, and that little electron that's off on his own, now he only has 1 negative and he has no positives, so he's negative. Before the dental radiographer can understand how X-rays are produced, a working knowledge of how ionization and the difference between radiation and radioactivity is necessary. All right, so in the atom, if it gains an electron, it's going to have a negative charge. If the atom loses an electron, it's going to have a positive charge. If an atom that gains or loses an electron and it becomes electrically unbalanced, it's called an ion, and that will probably be on your boards. So when we look at this picture, the ejected electron off on its own, if it goes and joins another atom and it unbalances them, so now it has 1 too many electrons versus the number of protons it had before, it's going to be a negatively charged atom. If that little ejected electron just stays all by itself, it's also still a negative ion because it doesn't have any protons to balance it out. The little remaining atom, because it's lost one, it now has two positive protons and one negative electron, and so it has a positive charge, and it is now a positive ion. That little X-ray photon that's coming in, that little wave, and then it hits the little electron and it falls off, that comes from the tube head of the X-ray machine, and we'll get into more how those X-rays are sort of shot at the atoms and how they break off those little ejected electrons. Okay, so ionization is the production of ions, or the process of converting an atom into an ion. When an electron is removed from an atom in the ionization process, an ion pair results. That will probably be on your boards. The atom that lost the electron is now a positive ion because it has too many positives, right? It has too many protons and not enough electrons. The ejected electron out on its own, it becomes a negative ion. I've said that a few times as well, so that will probably be on your quiz. Hint, hint. Okay, so radiation and radioactivity. There's a very big difference between these two. Radiation is the emission and propagation of energy through space or a substance in the form of waves or particles. And we talked about that before in the last chapter. Radiation is any type of energy that is passing through space or a substance in the form of waves or particles. Radioactivity is going to be the process by which certain unstable atoms or elements undergo spontaneous disintegration or decay in an effort to attain a more balanced nuclear state. So, what happens is when we are shooting those photons at atoms and they lose electrons, if they lose too many electrons, then they're very unbalanced. They're way too positive. And in doing so, in trying to find other electrons, the whole atom will actually just fall apart because it's lost a lot of its binding energy. These two things are often interchanged and they shouldn't be. The difference between radiation and radioactivity is very different. Also, I should have mentioned in that last slide that in dentistry, X radiation is used, but radioactivity is not used. We do not expose anyone to that much radiation that it would cause radioactivity. Here we have ionizing radiation, and this is radiation that is capable of producing ions by removing or adding an electron to an atom. That will probably be on your boards. It's classified into two groups. There is particulate radiation, and then there is electromagnetic radiation. So, particulate radiation are tiny particles of matter that possess mass and travel in straight lines and at very high speeds. There are four types of particulate radiation. All right, so electron particulate radiation has two different types, and they only differentiate in where they originate. So beta particles are fast-moving electrons emitted from a nucleus of radioactive atoms, but we do not use that kind in dental x-rays. Cathode rays are streams of high-energy electrons that originate in an X-ray tube. Electrons are emitted by a manufactured device. So cathode rays are man-made form of beta particles, but because they're different, they're not called the same thing. Alpha particles are the second type of particulate radiation, and they are emitted from the nuclei of heavy metals. They exist as two protons and neutrons, and they have no electrons. All right, so the third type of particulate radiation is protons, and it is essentially a hydrogen nuclei. It has a mass of 1 and a charge of +1. It's just one proton and one neutron caught together. They have no electron, and because it has no electron, it has a positive charge, and it is basically running around trying to find an electron. The neutron is the fourth type of particulate radiation, and it has only one nucleus, or one neutron in its nucleus. It's lost its protons, it's lost its electrons, and it has a mass of 1. It has no electrical charge whatsoever, and it's just a part of an atom. And then here we have electromagnetic radiation. It is the other type of radiation, the other type of ionizing radiation, right? We have particulate radiation and we have electromagnetic radiation. This one is the propagation of wave-like energy. It has no mass and it's traveling through space or matter, probably be on your boards. This one has an oscillating electric and magnetic fields that are positioned at right angles to one another. Electromagnetic radiation is made up of photons that travel through space at the speed of light. It's in a straight line with wave-like motion. That really doesn't make a lot of sense, does it? It is traveling through, but it's traveling in one direction. It's just moving in a wave-like motion. Okay, so this is probably my favorite visual aid for understanding electromagnetic radiation. First, they can be artificial or naturally occurring. Humans are very capable of creating electromagnetic radiation, and they're arranged here on this electromagnetic spectrum according to their energies. So if we just draw a little line right here in between visible and ultraviolet, we can see here that everything above this line is non-ionizing, and everything below this line is ionizing radiation, and that's going to be very important for us later. Electromagnetic radiation, they all have common characteristics, and they can be classified as ionizing or non-ionizing, as we saw in that last slide. Only high energy radiations are capable of ionization, and they're believed to move through space as both a particle and a wave. Both concepts must be considered. So when we're looking at our dental X radiation, we have to think about it in both that it's energy traveling in waves and it's also particulate radiation traveling in straight lines, and it's going to be that electron particulate radiation. So the particulate concept characterizes electromagnetic radiation in terms of discrete bundles of energy, which are called photons or quanta. Photons are bundles of energy and they have no mass or weight. Photons travel as waves at the speed of light and move through space in a straight line. They carry the energy of electromagnetic radiation. A photon is a bundle of energy that has no weight or mass and has the ability to collide with electrons found in the outer orbital shells of otherwise electrically stable atoms, which result in ionization when an electron is lost. Okay, so here we can see that wave concept. The characteristics of electromagnetic radiation as waves. We have a velocity, which is how fast that wave is moving. And then we have wavelength, which is the distance between the crest of one wave and the crest of the next wave. It is not the distance between waves. It is the distance between the crest of one wave and the crest of the next wave. The frequency is the number of wavelengths that pass a certain point in a given length of time. So when we look at the difference here, we can see long wavelength and short wavelength. The long wavelength is almost kind of lazy. It's just barely moving along. And the short wavelength, see how much more distance it has to travel? It's very fast. It's got to go up and down about way more times, probably 3 or 4 times by the time that other wave finally gets up to its crest. Wavelengths are measured in nanometers, which is 1 billionth of a meter. The shorter the wavelength, the greater the penetration, which means if it's a shorter wavelength, it's traveling faster and it has more power and it has a greater penetration. Conversely, the longer wavelength is traveling slower and it has less penetrating power. This is very important for us for our dental x-rays. Okay, so now here we're going into this next section of the chapter, and the learning objectives for this second portion will be to list the properties of X radiation, to identify the component parts of the X-ray machine, to label the parts of the dental X-ray tube head and the dental X-ray tube, to describe in detail how dental X-rays are produced, and to list and describe the possible interactions of X-rays with matter. I think this picture is so funny. So, X radiation is high energy, ionizing electromagnetic radiation. X rays are weightless bundles of energy without an electrical charge that travel in waves with a specific frequency at the speed of light. X ray photons interact with the materials they penetrate and cause ionization. Okay, so every X-ray machine that you'll come across has three separate component parts. It has a control panel, an extension arm, and it has a tube head. And even though it may vary in size and appearance, every machine you run into that takes a dental X-ray, that shoots dental X-rays, will have these three component parts. First, we have the control panel, which has an on-off switch. That's handy. It has an indicator light, and it has control devices. Sometimes it will have kilovoltage and milliamperage, and we'll get into that more. And every single control panel is going to have some type of settings where you can change the amount of time. And then it's going to have a plug because it needs to be plugged into an electrical outlet. So the portion, usually it's mounted on the wall, that allows the operator to turn the machine on or off and adjust the exposure time is called a control panel. Next, we have the extension arm. The extension arm suspends the X-ray tube head and allows for us to move that tube head around. It houses the electrical wires that extend from the control panel to the tube head, and it allows for the movement and positioning of the tube head, which I just said. What portion is the extension arm? The portion that connects the tube head to the control panel, allowing for horizontal and vertical changes in the tube head. Okay, so here we have the tube head. This is a very complex little part of this thing. The tube head is a tightly sealed, heavy metal housing, which contains the X-ray tube that produces dental X-rays. It has the metal housing, which surrounds the X-ray tube and transformers, protecting the tube and grounds high voltage components. So if for some reason the X-ray tube were to be fractured or damaged in some way inside the tube head, that metal housing is going to ground any of those things and keep everyone safe around it. That all of that blue area in this picture, that is the insulating oil, and it surrounds the X-ray tube and transformers, and it prevents overheating. So that oil, every single time you take a radiograph, is absorbing that heat. The part of the dental X-ray machine that is lined up with the film holder and directed toward the patient's face, it contains all of that wonderful tube head material, is called the tube head. And this picture you're going to find on page 13. We're actually going to have a worksheet where you're going to fill all of this out when you come to lab. So be prepared to fill all of that material out. All right, so more inside the tube head. It has the tube head seal, which if you look, you see like as the positioning indicator device, if you look up, you can see the aluminum discs, and above that, you see the tube head seal. That tube head seal permits X-rays from exiting the tube head. It seals the oil in, and inside the tube head seal, it has those aluminum discs, which filter the X-ray beam. The X-ray tube inside that part of the blue, that has all of the X-ray generating system, and it is kind of like the heart inside this tube head. And then we have the transformers, and they alter the voltage which of the incoming electricity so that the X-rays are created at the appropriate voltage. Continuing with the tube head, we have the aluminum discs. Remember, inside the tube head seal, there were those aluminum discs. They filter out the non-penetrating longer wavelengths. So wavelengths that aren't traveling fast enough will hit those aluminum discs and actually be unable to go through. Whereas the faster, more powerful, shorter wavelength, penetrating wavelengths will go through those aluminum discs and on out to the patient. The lead collimator is going to restrict the size of the X-ray beam. And what it does is you can see there in the circle, only the X-rays that go through the center will be able to continue going. All of the X-rays that hit the outside, those ones that are going outward, they will not be able to continue down toward the patient. The positioning indicating device, the PID, is what aims and shapes the X-ray beam. And so that is what we actually point toward the patient, and we line it up with our receptor in order to be able to point those X-rays toward that receptor and get the shot that we're looking for. All right, So now we're at the X-ray tube, and this little glass cylinder with the cathode and the anode, that is where all of the magic happens. This is where the X-rays are actually created. The entire tube is sealed inside a glass vacuum tube, and what that means is that there is no air inside that tube. It is measured several inches long by 1 inch in diameter. It includes the lead glass housing or the leaded glass housing, what we can see through right there, the cathode, and the anode. So that leaded glass housing, that is the glass that you're looking at right there. Only it's because it's clear, it looks like maybe it's not leaded, but it's actually only a little tiny window is where the X-rays are actually able to escape. All of the other X-rays that are created, those that scatter and that go out in the other directions, the ones we don't want them to go anywhere, those actually hit the glass, and because it's leaded, they don't actually get to escape. Um, so that tube prevents them from escaping. That's going to be on your boards. One little area has that little window, and that's what's going to allow those X-rays to go through. They'll go through the tube head seal. They will go through the aluminum discs. They'll go through the lead collimator, and then they'll go out the PID on towards the patient. Okay, so now we are at the cathode, and we are inside the tube here, that vacuum tube. This is where everything sort of begins. The cathode is negative. Okay, it's very important. That will probably be on your board exams, that the cathode is negative, and it consists of a tungsten wire filament and a molybdenum cup. If you kind of tilt your head to the side, to the right, it looks kind of like a little skate ramp, right? That little cup. It's also called here, it's labeled the electronic focusing cup. That's also called the molybdenum cup. And electricity is shot through that little wire filament, and the heat from that is actually where the energy comes from to break those electrons off of the atoms, and then the cup, that molybdenum cup, actually focuses those electrons and gets them pointed in the right direction over towards our anode. So it's very important that you remember that the cathode is negative, and the cathode is where the electrons necessary to generate X-rays come from. The cathode is where everything is started. Now, the hotter that we make that tungsten filament, the more heat that we produce, the more electrons that are produced, and the more X-rays that are produced. The tungsten filament produces those electrons when heated, which is also known as thermionic emission. And we already talked about it before, that the insulating oil inside the tube head, that's what's going to absorb that thermionic emission heat. And then here we have the molybdenum cup, focuses electrons into a narrow beam and directs them toward that tungsten target, which is in the anode. All right, so those electrons are sent over from the cathode to the anode, and the anode is positive. So this positive electrode, which will probably be on your boards, it consists of a wafer-thin tungsten plate, which is embedded inside a solid copper rod. That when those electrons hit into that tungsten target, they actually are where the electrons are converted into the X-ray photons, okay? The tungsten target serves as the focal spot, and that is where everything switches over and those X-rays become, those electrons now are X-rays and they are photons. The copper stem functions to dissipate heat away from the tungsten target. The whole purpose of that copper stem is to actually absorb some of that heat energy, and the oil around as well is also going to absorb a lot of the heat. Most of the X-rays that are created at that collision point when those electrons strike that tungsten target, 99% of those X-rays are actually just absorbed by the copper stem, and then they are dissipated in heat. Now, only 1%, this will probably be on your quiz and your final and probably your boards, that 1% is what is actually directed outside of that window and is directed out toward the patient. So of all of the X-rays, photons that will be created in that split part of a second when the electrons hit that tungsten target, only 1% of them will actually continue on toward the patient. Okay, so here's where things get a little bit harder to understand when we start bringing in electricity and electrical currents, but I want you to just try to stay with me. So the X-ray generating apparatus is using electricity and electrical currents. We're going to be using circuits and we're going to be using transformers in order to understand how that electricity enters the tube head and then sends that current through that tungsten filament in the cathode in order to create X-rays, right? We have to understand how electricity goes into the tube head, how it's converted, and then how that electricity then leaves the tube head, right? Okay, so here we go. Okay, so you remember when we were talking about particulate radiation and how there's those two different types of electron particulate radiation. We have the beta, which are made from radioactive atoms that is totally naturally occurring and is not man-made. And then we have the cathode rays that are human-made and it's made through high-speed electrons. We are able to create that. Humans are able to create this particulate radiation because of electricity. And electricity is where we get our energy that we need in order to make X-rays. That energy is what breaks those electrons off and sends them toward that tungsten target. So the electrical current, which is a flow of electrons through a conductor, is where we get our energy and where we break those electrons off and where all of everything sort of starts. All right, so there are two types of electricity. We have direct current, or DC, and this is when electrons are flowing in only one direction through a conductor, which is any type of material that conducts electricity, of course. And then we have alternating current, or AC, and this is when electrons can actually flow back and forth and they go in opposite directions. Rectification is when we convert that alternating current to direct current. And the dental X-ray tube itself acts as a self-rectifier in that it changes the AC to the DC when it's going to produce an X-ray. This ensures that the current is always flowing in the same direction, or more specifically, from the cathode to the anode. Amperage is the measurement of the number of electrons moving through the conductor. And then current is measured in amperes or milliamperes. Voltage is the measurement of electrical force that causes electrons to move from a negative pole to a positive one. Voltage is measured in volts or kilovolts. Here you can think about it like as if it were water, right? With amperage, we would have more water volume traveling in the stream. If we were talking about voltage, we would have a faster moving current. It would be like white river rafting sort of water. So amperage talks about volume, whereas voltage talks about speed and power. In the production of X-rays, both amperage and the voltage can be adjusted. All right, so this picture here is exactly what you're going to see when you are making those adjustments for your radiographs. You can see that it has the KVP control, which you can change from 60 to 70. And then at the bottom, you can see the MA setting that we cannot change. These X-ray control panels are completely set at 7 MA. So in milliamperage adjustment, you could increase or decrease the number of electrons passing through the cathode filament. However, ours at Concord will not let you. And then kilovoltage peak, the KVP adjustment, we can control the current passing from the cathode to the anode. All right, so we use two types of circuits in dental radiology. There is the low voltage circuit, which is also called a filament circuit, and it uses 3 to 5 volts. It regulates the flow of electrical current to the filament. It's controlled by the milliampere settings. And then the high voltage circuit, which uses 65,000 to 100,000 volts, and it provides high voltage required to generate X-rays. It's controlled by the kilovoltage settings. What happens is when you turn that X-ray machine on, that filament circuit, that low voltage circuit, is going. It's causing energy to go through that tungsten filament, and it's creating an electron cloud around that tungsten filament, and it's just kind of hovering there right next to the molybdenum cup. And then when you press the exposure button, that high voltage circuit snaps on, and it's what shoots those electrons from that cloud over toward that tungsten target in the anode. The transformers that are inside the tube head are used to transform, essentially, the electrical current. We have the step-down transformer, the step-up transformer, and the autotransformer. They do what they sound like they do. So the step-down transformer takes that incoming 110 to 220 line voltage, and it pulls it down to that 3 to 5 volts that we need in the low voltage circuit. The step up transformer is what takes that incoming 110 to 220 and pulls that power up to the necessary 65,000 to 100,000 volts that we need for the high voltage circuit. The auto transformer is the one who makes those very minor adjustments in the fluctuations for both the step up and the step down transformers. Okay, so the step-down transformer is used to decrease voltage from the incoming 110 to 220 line voltage to the 3 to 5 volts that we use in the filament circuit. There are more wire coils in the primary coil than in the secondary coil, and the primary coil is what is slowing those electrons down, the electrons that are traveling in that circuit. It's going to slow them down so that only 3 to 5 volts are what's passing through the filament. The step-up transformer is what is used to increase the incoming voltage from the 110 to 220 line voltage up to the 65,000 to 100,000 volts that are necessary for the high voltage circuit. And this is done by having more coils in the secondary coil than in the primary coil. So in the primary one where it's entering, there's actually not very many coils with it that the voltage has to travel through, and that allows those electrons to speed up. Okay, and the auto transformer, it does exactly what it sounds like it does. It serves as that voltage compensator, and that corrects for those minor fluctuations in the current. We don't really have to get in any deeper than that. That's plenty. So now that we understand the way that those X-rays are produced and how that electricity is used in the production of those X-rays, now we're going to start talking about the production of X-rays. So what happens in between the anode, in between the cathode and the anode. We'll talk about the different types of X-rays that are produced, and we'll go into more definitions of X radiation. All right, so here's what we touched on a little bit before. The electricity from the wall comes into the X-ray unit. The current is directed from the filament circuit and the step-down transformer in the tube head. And basically, that's what's going to cause that cloud. The filament circuit uses the 3 to 5 volts. Once it's traveled through that step-down transformer, it only has 3 to 5 volts now. It's going to heat that tungsten filament up in the cathode, and you can see that little cloud of electrons floating around that tungsten filament. The thermionic emission does occur, and some of that is released and it is absorbed by the oil. All of this takes place without ever having to press the exposure button. Due to the energy used simply by keeping the machine on, the unit should be turned off every night, and ideally anytime you're going to be not using it for long periods of time. Those electrons that are forming in that cloud, sitting in that molybdenum cup, stay in that cloud until the high voltage circuit is activated. And this is activated when you press the exposure button. The molybdenum cup of the cathode then directs those electrons toward the tungsten target in the anode. When those electrons strike the tungsten target, less than 1% of the energy is converted into X-rays, and the remaining 99%, which we talked about before, is actually just lost as heat. It gets absorbed by that copper stem and it gets absorbed by that insulating oil. So how long does this take for it to happen? It actually happens in much less than 1 second. The operator should remind the patient to stay as motionless as possible, at least until the end of that beep is heard, because even the smallest movement will distort the image and most likely result in a retake. Okay, so the small number of X-rays that are produced once they shoot those electrons over towards the tungsten target, that 1% is made, right? And some of those are directed by the shape of the anode. It's directed toward that little window in the unleaded glass. So the leaded glass of the whole tube, there's a little window of unleaded glass that allows the X-rays to go through. The X-rays travel through there, they travel through the tube head seal, and then they travel through the aluminum discs. And those aluminum discs are filtering out those slower, longer wavelengths that are less penetrating. The size of the X-ray beam is restricted then by the lead collimator and by the lead-lined PID. This helps to direct the beam of X-rays directly where the operator wants those X-rays to go. Why are those longer wavelengths removed? Because they are less penetrating and thus they are not useful for dental radiography. Here we have the two different types of X-rays that are produced. We have the general radiation or breaking radiation. You'll also hear this referred to as Bremsstrahlung radiation. And then we have characteristic radiation. These two differ in their energy and their wavelength. This is where that kinetic energy of the electrons is actually converted into those X-ray photons. Okay, so in general radiation, the electrons, that high volume of electrons that are traveling down the tungsten and they hit into that target, they undergo not one, but many interactions with the target. Most of the X-rays that are produced here, about 70% of them, are produced in this way. And it's produced when the electron hits the nucleus of a tungsten atom or it passes very close to the nucleus of the tungsten atom. That term breaking actually refers to the sudden stopping of high-speed electrons once they hit the tungsten target in the anode. The electron actually rarely hits the nucleus of the tungsten target, but when it does, all of its kinetic energy is converted into a high-energy X-ray photon. Okay, so the other type of radiation is this characteristic radiation, and this is produced when that high-speed electron dislodges from an inner shell electron. When the high-speed electron dislodges that inner shell electron. So you can see here that the bombarding electron is going in straight and then it's kicking out one of those ejected electrons. Only very high-speed electrons would be able to go all the way through and have enough energy to break off one of those inner shell electrons. Those, remember, they have a lot more of that binding energy holding them in there. So the remaining orbiting electrons will actually have to completely rearrange themselves in order to fill up that vacancy where that inner shell electron is missing. This will only occur at 70 kVp and above, and that is because it takes something traveling very fast with a lot of that kinetic energy in order to be able to break that binding energy of that inner shell electron. The characteristic radiation actually only accounts for a very small part of the dental X-rays that are produced in the dental machine. Okay, so once those electrons have been converted into X-rays, and we know that the two types of X-rays were general X-rays or general radiation and characteristic radiation, here's what happens to it once it has become radiation. So first we have primary radiation, which is the penetrating X-ray beam that is produced at the target of the anode. Primary radiation can also be referred to as the primary beam or the useful beam. Secondary radiation is radiation that is created when the primary beam interacts with matter. Matter includes the soft tissue of the head, the bones of the skull, and the teeth. Anything that it touches, right? Any liquid, gas, or well, not gas, but liquid or solid that the X-rays touch, that is secondary radiation as it's passing through. And then we have scatter radiation, which is a form of secondary radiation, the result of an X-ray that has been deflected from its path by an interaction with matter. Scatter radiation, no matter how fast it is traveling, is detrimental to both the patient and the radiographer. So it is very important to follow the proper precautions. It means you don't stand in the room, even if you're not there where the beam is pointed, if you're not in the primary radiation or even the secondary radiation, if you're there picking up scatter radiation, it is still harmful to your health. And it is why we want to reduce the number of x-rays, the number of radiographs that we need to take on our patients, because we want to reduce the amount of scatter that they are exposed to. When that radiation interacts with the patient, one of four things can happen. Either no interaction, the matter will absorb the energy and the photoelectric effect. We can have a Compton scatter, or we can have a coherent scatter. When X-ray photons arrive at the patient with energies produced by the dental X-ray machine, one of these will happen. So that first one is that there is no interaction with the matter that the photon is passing through. The X-ray photon passes through the atom unchanged and leaves the atom unchanged. These photons are responsible for producing the densities on film and making the dental radiography possible. So what happens, we'll get into it more later, but the photon passes through the matter and touches the sensor that we are, either the sensor or the film that we're using, and it actually is what leaves that black or that darker color in our radiograph images. It is possible for an X-ray photon to pass through matter without an interaction. Then we have the absorption of energy and the photoelectric effect. So the X-ray photon is completely absorbed within the matter or the tissues of the patient. So the first one is the absorption, the total transfer of energy from the photon to the atoms of the matter. In this one, they don't harm the atom that they are colliding with at all, but it just doesn't have enough power to affect the atom. So maybe that the photon collides with those electrons, but the binding energy of the shell is actually higher than the amount of energy that the photon has. And so in that case, it would be absorbed, but it would not affect the atom. Then we have the photoelectric effect, which is when an X-ray photon collides with a tightly bound inner shell electron and gives up all of its energy in order to eject the electron from its orbit. That ejected photoelectron is absorbed by other matters. And this actually, the photoelectric effect, accounts for 30% of the interactions of the dental X-ray beam. Next is Compton scatter. Here, the X-ray photon is deflected from its path during its passage through matter. In Compton scatter, ionization takes place when the X-ray photon collides with a loosely bound outer shell electron and gives up part of its energy to eject the electron from its orbit. The X-ray photon loses energy and continues on in a different path, like in a different direction, but at a lower energy level. And then that little electron that got popped off from that outer shell, that ejected electron is now called a Compton electron, and it is negative, of course. Compton scatter accounts for 62% of the scatter that occurs in a diagnostic radiography. At the atomic level, the Compton effect accounts for most of the scatter radiation. You will probably see that on a quiz or your final or your boards, so I would pay attention to that one. At the atomic level, the Compton effect, which is Compton scatter, When the X-ray photon knocks that electron off, the electron becomes a Compton electron. This is the Compton scatter when the photon continues in a new direction, and all of that together is the Compton effect. Next, we have coherent scatter. And coherent scatter is when an X-ray photon has its path altered by the matter. The low energy X-ray photon interacts with an outer shell electron. No change in the atom occurs, and the X-ray photon actually still has energy, so it continues on, but in a new path. The coherent scatter is also known as unmodified scatter. The X-ray photon simply changes direction without a change in energy. Thus, it is unmodified. Coherent scatter accounts for only 8% of the interactions of the dental X-ray beam with matter. So this is important that we understand that it doesn't affect the cell and it doesn't affect the energy. It just changes direction. All right, so that is the end of chapter 2. Again, if you have questions, please post them in the discussion board Q&A, and if it is of a personal nature or if you need to ask me something directly, feel free to send me an email.